So just going to run through a couple of things that might show up on the exam uh, that haven't been covered in other videos someplace. So from Chapter 2, the matrices and Gauss-Jordan and things like that. So here we have a system of equations, and I may ask you to write this as an augmented matrix. And what you'll do is simply the entries in the matrix are the coefficients of the equations, and then in the right column of the augmented matrix is the what's in the equals, on the other side of the equals sign. And there we have an augmented matrix. And then I may say to you, okay, here's what I'd like you to do. You've got this augmented matrix. What I'd like you to do, Gauss-Jordan, I want you to take care of the first column so that we've got a, 1 in the top left and then zeros below it. So what are the steps, Gauss-Jordan, that get us there? So we can say the first thing we do is take row 1 times 1/2, and that becomes row 1. So row 1 is 3/2, 1, 3/2, and then we'll multiply row 1 by 3, add it to row 2, and that'll be the new row 2. So multiplying this new row 1 by 3, we would have 3 9/2, 3 9/2, and we're going to add that to the second row. So adding 3 to -3 in the first column, we have 0. Adding 9/2 to the second column, we get 7. And adding 3 to the third column, and multiplying the last column by 3, this. And then for the last row, we can take row 3, subtract row 1, and have that be the new third row. And so we subtract 1 from 1, we get 0. Subtract 3/2 from 2, and we get 1/2. Subtract 1 from -3, we get -4, and subtract 3/2 from 6, and we get 9/2. So there we've got a 1 up here, and then zeros below. And then one last thing we might do with Gauss-Jordan. What's the solution to a system of equations that has this final matrix, augmented matrix? Well, that's x equals -7, y equals 3, and z equals -2. Because this first row represents, if we have columns x, y, z, and equals, we've got 1x plus 0 equals -7, 1y equals 3, and 1z equals -2. So that's what we might see with Gauss-Jordan and augmented matrices. Something else from Chapter 2, we've got matrices. So we've got 2 matrices here. Let's say matrix S is a sales matrix. So thinking about the problem we had in the graded problem, you've got 3 stores and you sell 3 kinds of pizza. So we've got here store 1, 2, 3 pizza, type 1, pizza type 2, pizza type 3. And then we've got a cost matrix, a matrix C, which says how much each pizza costs. So pizza 1 costs $20 to make, pizza 2 costs $15 to make, 3 costs $25 to make. Let's say we want to find the product S times C. Okay, so we've got a 3 by 3 matrix and a 3 by 1 matrix. This tells us, since these numbers are the same number of columns in S as there are rows in 3, and then our product will be a 3 by 1, so 3 rows, 1 column. And to multiply, we multiply the first row times the first column, and we get 100 times 20 plus 150 times 15. Oops, 2,000 plus 200 times 25. And that's 50. Again, second row times first column will give us the entry in the second row in the first column. So 200 times 20 plus 200 times 15 plus 200 times 15. Oops, sorry. 200 times 20, 200 times 15, 200 times 25. That's actually 5,000, sorry. And that gives us 12,000. And then third row times first column, 100 times 20 plus 300 times 15 plus 200 times 25. And that's that. So I may ask you, what does this matrix mean, or what does this entry represent? Well, if we're multiplying, each row is stores and the columns are cost, this is going to be the total cost for store 2. So here we've got each entry, we've got 200 times 20, that's 200 pizzas times the cost to make that kind of pizza. Here we've got 200 pizzas times $15 per pizza, and then the last entry, 200 times 25, is how many pizzas at store number 3 and how much it costs at store number 3 to produce. Okay? That's what this particular entry means. Second row, first column means the product of the second row and first column here. The rows represent, if we think about the final product, the rows from S represent stores. So these are stores, 1, 2, 3. And the columns from matrix C represent cost to make. So this is total cost at each of the 3 stores. So talking about probability, here are some things we should be familiar with. So in general, this is how we can describe the probability of event. So the number of ways for, so the probability of event A is the number of possible ways A can occur divided by the total possible outcome. So for example, if I said, what's the probability of rolling a die and getting an even number? Well, it's going to be 3 out of 6, because there's 3 possible ways you can get an even number by rolling a 2 or 4 or 6. And there's 6 possible outcomes, each of the 6 sides of the die. If I said, what's the probability, so I put all the days of the year into a hat or a box or something. And let's say, nothing against February 29th, but let's just say we have 365 days. Put each of those dates into a box and we pull one out. So what's the probability of picking a day in January? Well, that's how many ways we can pick a day in January. And there's 31 days in January and 365 days in all. So that's the probability of drawing a date out of the hat and having it be a day in January. Something you want to be careful with, something like this. That probability is not 1 out of 12. Okay, we might think, okay, January is one of the months out of 12 months, but if we're talking about days, there are 31 pieces of paper or cards or whatever it is in the hat that have a day in January on them, and there's 365 days in all. So let's not do that, and we'll do something like that. So probability of A and B. Now we talked about sets. That would be the probability of A intersection B, or the probability of two things happening at the same time. Probability of A or B means A happens or B happens, or they both happen. And this we can say is the probability of A plus the probability of B minus the probability of A and B. So if we think about this in terms of Venn diagrams, let's say, we have probability of A, here's the probability of B. What ends up happening is we double count here, or we count these elements with A and we count those elements with B. So this subtraction at the end takes care of counting that twice. We only count it once. So if I said, what's the probability of drawing a card out of a deck and getting the 3 of hearts? So here's the hearts, and here's the 3s. So we've got ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So we've got the 13 heart cards, including the 3 of hearts. And then the threes, we've got the 3 of diamonds, the 3 of spades, the 3 of clubs. So the probability of A or B would be 13 hearts out of 52 cards plus 4 out of 52 threes minus 1 out of 52. So the probability of drawing a heart or a 3 ends up being 16/52, or reducing that 4 out of 13. Okay, so here what this means is there are 16 distinct cards that are hearts or 3s. So the 13 that are hearts plus the extra 3 3s that aren't hearts. Okay, so we add the hearts, we add the 3s, but we subtract the 3 of hearts, which would get counted twice. Okay, so that's an OR situation. And then the probability of A given B, that conditional probability, is simply number of ways to get A and B divided by the number of ways to getting a 3, given that it's taking a card from a deck of cards. What's the probability that we get a 3 given that it's a heart that we draw? Well, that's a number of ways to get the 3 of hearts over a number of ways to get hearts. So that's just 1 out of 13. The idea behind the conditional probability is you only care about a certain part of your population. So if I was looking at a class and I wanted to know what's the probability that someone smokes given that they're from Walla Walla, let's say. So probability maybe smoke given that the person's from Walla Walla. That means how many smokers that are from Walla Walla divided by people from Walla Walla. So it doesn't matter about students from other places. We're only concerned about those from Walla Walla. So that becomes our new population in a way. The new group we're looking at, of those people from Walla Walla, how many of them smoke? That's a conditional probability. Last couple of things, the idea of mutually exclusive. One. Mutually exclusive means can't happen at the same time. Okay, so for example, the probability that you were born in Washington, so event W is born in Washington, event M is you're born in Michigan. W and M are mutually exclusive events. You can't be born in Washington and in Michigan. Okay, you're born in one or the other. Okay, you can't be both. The probability of being over 6 feet tall and under 6 feet tall, those are mutually exclusive events. They can't happen at the same time. And then the idea of independence. Independence doesn't mean a lot of times people confuse it for being mutually exclusive. Independent, they're independent of one another, two events. In statistical terms, what independence means is they have no effect on each other. Okay, so if two events are independent, it means they don't affect one another. So in the example of cards, drawing a 3, that's one event. Another event is drawing a red card. These two events are independent, which means my chances of getting a 3 aren't any different if I draw a red card than if I draw a black card. And there's just as many black 3s as red 3s. So drawing a 3, the probability isn't going to change depending on the color. Likewise, depending on what color I draw, I'm no more or less likely to draw a 3. If I draw a red card, I can draw a couple of different 3s. If I draw a black card, I can draw a couple of different 3s. So these would be considered independent events. A case where you might see events that are dependent. So let's say smoking rate of females is 22% and smoking rate for males is 47%. We might say that smoking and gender are dependent, because it seems as if males smoke at a higher rate than females do. If they were independent, it would mean whether you smoke or not isn't affected by gender. Now, in terms of this effect, we mean correlation, which means they're related somehow. It doesn't mean that being a particular gender makes you smoke more. It just means there's a relationship between those two variables. And so it seems that males smoke at a higher rate than females. It doesn't mean that there's anything genetic that causes men to smoke more or make females smoke less. It's just there's some relationship there. Okay? So those are two concepts that you should be aware of in terms of probability. And then the last thing to talk about is counting principles. So combinations, permutations. And the main thing here order does not matter, and here order matters. So for example, if I have 30 students and I want to pick 4 of them, how many groups of 4 can I come up with? Well, whether it's a combination or permutation depends on what other information we have. So if I say I want a group of 4 to represent class at a meeting. Here, there is no order. I'm just taking 4 people. So it doesn't matter if I'm taking student 1, 2, 3, 4, or student 4, 1, 2, 3, or student 3, 1, 4, 2. The order doesn't matter. I'm taking 4 of them, sending them to the meeting. So how many ways can I choose a group of 4 out of 30? Well, that would be 30 times 29 times 28 times 27 over 4 times 3 times 2 times 1. Okay? If I wanted to take a group of 4 to be president, vice president, secretary, and treasurer of the class, this would be a permutation because the order of the students matters. So having student 1, 2, 3, and 4 is different than having student 3 be president, student 1 be vice president, 2 be secretary, 4 be treasurer, or 4 president, 3 vice president, 1 secretary, 2 treasurer, etc. So there the order matters. So how many students how many different student governments could I take from that group of 40? Well, it would be 30, because I could have 30 possible presidents times 29, because once I've chosen a president, there's 29 students left to be vice president, times 28, because after picking these 2, there are 28 students left that can be secretary, and then after I've taken the first 3, there's 27 students left to be the treasurer. So that's how many permutations we can have. This calculation right here gets at a general counting principle. So how many ways can an event occur? So say I've got a license plate. So I've got a letter, and a number and a number and a number. That's a license plate. How many possible license plates can we choose? Well, if we can repeat numbers and letters, I can have 26 possible letters for the first letter, times 26 possible for the second, times 26 possible for the third, times 10 numbers for the first, 10 for the second, 10 for the third. That's how many ways I can possibly have a particular license. Suppose I want to choose an outfit, and I've got 3 pairs of pants and 3 shirts and 2 pairs of shoes. How many possible outfits will I have? Well, 3 possible pants can be paired with 3 possible shirts, 2 possible pairs of shoes. I've got 18 different outfits I can wear. How this comes up is, first I'm choosing pants. I've got 1, 2, 3 pants. With each of those pairs of pants, I can wear shirt 1, 2, or 3. Shirt 1, 2, or 3. Shirt 1, 2, or 3. And then with each shirt and pant combination, so here, pant 1, pant shirt 2, pant 1, shirt 2, pant 1, shirt 3. Each of those I can pick one of the 2 pairs of shoes, etc. So I've got an outfit, 1 pair of pants, pant type 1, shirt type 1, shoe type 1. And then pant 1, shirt 1, shoe 2. I've got pant 1, shirt 2, shoe 1. Pant 1, shirt 2, shoe 2, etc., etc., etc. So I've got all these different combinations, and that, if we listed them all out down to pant 3, shirt 3, shoe 2, we'd have a total of 18. So that's a basic counting principle. So if I've got my pants are blue, gray, or tan, and then my shirts are white, blue, red, and my shoes are black, brown. And I want to know what's the probability that I randomly select an outfit and I've got blue pants, a white shirt, and brown shoes. Well, how many ways can I get this arrangement or this particular outfit? Well, there's one possible way I can get that. I select my blue pants, my white shirt, my brown shoes out of 18 possible outfits. So that's a probability of getting any of those particular outfits. I've got a 1 in 18 chance of choosing them. So this is the kind of stuff you're going to see on your final. And there you have it.